Hi, I'm Malte. I'm data scientist at T-Systems, and today we want to talk about edge computing and 5G and how we can use it to enable our AI applications. So to fulfill all these non-functional requirements that come when we want to deploy an ML model. So it's about latency, it's about privacy, it's about scalability and manageability. All these tasks that are critical if you want to get your use case into production. So what is the agenda for today? First, we want to discuss what is edge computing, what is 5G, and how does it help us. Second, we want to have a look at some example use cases. And third, we want to talk about architecture and what the architecture with edge computing could look like. But before we start, I'm available during the whole presentation. So if you have any questions or comments, don't hesitate to use the chat and drop me a message. I will be happy to come into a discussion with you. So what is edge computing? Edge computing is basically bringing the workload, the computation, as close as possible to where the data is generated. And when we think about data, we often think about data warehouses that are located in the cloud. But this is not where the data really comes from. The data is generated at cameras, at smart glasses, at AGVs, at sensors, all these devices that are becoming more autonomous and more connected. And what we previously referred to as IoT devices with limited compute power that become more advanced and more connected today. So let's refer to all of these devices as edge devices, devices that produce data, that observe and sometimes also influence the current state of the world, and that are influenced by us users in the environment and by other edge devices. As I said, these devices become more capable. So one possibility could be to deploy our models directly on the edge devices, like on a camera or on a smart glass. But as you see, these devices can be very heterogeneous. So, and not all of them have the capability to compute ML models to do inference. So we can use extra edge devices like from the Nvidia Jetson family that have accelerated computing and that can be directly connected to the edge device for doing the ML inference. And we will have an example of this architecture later. But think about an AGV, which transports goods from one point of your production chain to another. And it generates huge amounts of data, like its position, detected obstacles, information about the moved goods, and so on. And this information about the position and detected obstacles, for example, can be highly valuable for other edge devices, for other AGVs, because this information can be used for rerouting. So there needs to be some interaction, some centralized service to exchange and combine information from various sources. So that's where the cloud comes into play. It has great advantages of all the services that we have in the cloud, like Kubernetes, cloud services for training models. We have the hardware, we have the flexibility, the scalability. However, also in the cloud, there are some limiting factors. As I said, the number of connected devices is constantly growing, and in the same time, the amount of data produced by each of the devices is growing. And with the current technology, we are coming to a limit what is technically possible in terms of data transfer. And also, we could have issues with the latency. If data from one AGV has to be transferred to the cloud first, an inference has to be done, and then the inference has to be transmitted to the other AGVs that can have too high latency if there are services that guarantee the safety of all persons on the shop floor. And if sensor data is not processed and actions are not taken fast enough, that can be a risk. So, and furthermore, transferring data to the cloud can be a potential privacy risk. For example, due to GDPR, there are restrictions in transferring image data that has sensible personal data to the cloud. And also to secure business secrets, it might not be wanted to transfer sensible data to the cloud. So we now could accelerate all the devices with GPUs, which comes with high manageability costs. And in this case, we would only transfer pre-processed data, so only metadata to the cloud. So we are at a point where, on one hand, we want the scalability, the reliability, the flexibility of the cloud, and we want to make use of containerized applications in Kubernetes, not only Docker that might run in some of the edge devices, but not on all of them. But we still want the computational power as close to the edge device as possible. So one possibility is using edge servers. Edge servers are basically an intermediate layer, a server rack that is on-premise. It has the advantages of the workload on the edge, so very near to where the data is generated, but still has the easy management of your services, has Kubernetes, for example, can provide redundancy with multiple server rigs, and it can also take the workload from the edge devices, from the AGVs, for example. We have a POC here where the AGV is only having the camera, but all the decisions about routing are done on the edge server. And it can also do all the computation, for example, for AR glasses, which are currently often heavy. And if the computational power does not need to be on the device, but can be on the edge server, they can be much slimmer, but still work in real time, which would not be possible if the computation needs to be transferred to the cloud first, and then the inference has to be transferred back to the AR glass. And furthermore, cameras can be just cameras, which is much cheaper than having all cameras with dedicated GPUs for the inference. Furthermore, as this part here, the part below, is all on-premise, your data never leaves your network and is not transmitted via the internet at all. So it is much more secure. So does that mean we don't need the cloud anymore? Certainly not. The edge computing is an extension of the cloud, would never replace it. So we have the edge devices that produce data and that can take in some kind of autonomous decisions. We have the edge server that can manage the edge devices, can provide centralized services either for communication or for all ML tasks, basically, because it's close enough to to meet latency requirements. And we have the cloud still for training, for the management of the different facilities, for monitoring, for analysis, and all the services that we use in the cloud. So with edge computing, we are placing the workload as close as possible to the data and to where the data is generated. So we have now the GPU where the decision is taken, where your ML model runs, that can run either on the edge device or on the edge server. And second, to reduce latency and to get all of this in your campus, we need some kind of communication to get the data from the edge devices to the edge server, for example, and the decisions that are made by the ML model, by the GPU, and the actions that are taken back to the edge device. And that is where 5G comes into place. 5G is basically a new mobile communication standard that allows many of these use cases. It is the successor of 4G, and it provides a lot of advantages, like an increased number of devices. It can now handle up to 1 million devices per square kilometer. An increased capacity and data rates, as we saw before, the number of devices and the amount of data that has to be transferred is constantly growing. And third, the reliability and latency. The reliability is much higher and the latency is much lower. So what we basically have with 5G is more devices, more data with less latency. And in comparison to Wi-Fi, it provides higher security because stuff like man-in-the-middle attacks are not possible anymore. And problems like handover disconnects when switching between different access points do not occur. So it's perfect for example, AGVs with centralized control. So T-Systems has the 5G Campus Edge solution. And a 5G Campus Edge network provides a private cellular network where only your SIM cards, only your devices can use this Campus Edge. It's needed if you have if latency is absolutely critical, if offline capabilities are needed, if the data must not be transferred or over the internet for security reasons, for example, or if the volume of data is too big to be transferred. And in this private network, really only you have access. So there's no, you don't have to share the capacity with any other devices in the public 5G network. T-Systems provide a solution for that that is called the EdgAir ecosystem. It provides the system for edge computing for connectivity. So it has a base layer with connectivity on 5G networks where you can do real-time communication in your private campus edge network. It has a processing layer on premise, so your data is transmitted in real time to an edge server where AI applications can run on with accelerated computing using Nvidia GPUs. And it has an application layer on top where you can have managed Kubernetes, managed Cloud OS that enables all the use cases that has the tooling for data scientists or software developers to evaluate all the information that comes on site. And then it has applications built in like visual quality control on the edge, like autonomous guided vehicle, where all the computation takes place on the edge server, like AR and VR applications. So that was some theory, but how can we now use edge computing? What are applications for that? Do you have any ideas or questions? Then post them in the chat. Let's now talk about two use case examples. One with one edge device only, a Jetson Xavier AGX, and one with an edge server on a shop floor. So the first use case we all know, it's if you go by bus or by metro or by train, sometimes the bus or metro is completely packed, and sometimes you are the only one on the bus. Why is that? Maybe because the routes and schedules are not perfectly adjusted to the demand. So what public transport providers want to know is how many people are using their services at which time, to optimize their schedules to be more flexible. And also in Germany, they have to report on the usage of their vehicles to get subsidies from the government. So what they currently do is they create manual samples, meaning that there are employees that drive the bus and use clickers to count how many people are on the bus. There are also alternatives like to this manual counting, like laser scanners or laser sensors or photoelectric barriers, but these have to be built into the to the bus in every vehicle at every door, and that is not always wanted. But hardware that every bus or metro already has is cameras. And what we can do is use the camera stream to analyze and monitor people entering and exiting the bus. However, due to privacy laws, GDPR, we are not allowed to stream the video to the cloud. And furthermore, in a metro or in a bus, the connection can be very unreliable. So transferring the stream, the raw stream to the cloud would not be feasible. Instead, we are using an Nvidia Jetson AGX in the bus that relies on real-time processing of the video footage and only sends the metadata to the bus. So this is the very, very basic way that works. So as we are on a developer conference, let's have a look how our pipeline works, how our architecture works. So first of all, it's about developing the ML services. We have a platform there with an object storage, a database for all the data we collected. We have selection and data transference services, and then a data labeling tool where in this case we have to detect people. So it's about labeling the persons on the video footage. Then we have automated training pipelines that create after the tests a model and store it in the model registry. And second, encapsulated from that kind of the business logic that is also created in parallel, containerized, and pushed to a container registry. If we have a new model or if we have a new business logic, this is sent to an integration environment, basically a Kubernetes cluster where integration tests can be run, where unit tests can be run, and that is in this case where we are doing video processing running on DeepStream. If these tests are successful, the data is then, or the model is then deployed to a bus with a CI/CD pipeline. And in the bus, there is the Nvidia Jetson Xavier AGX, which is connected to all the cameras in the bus. It's getting the images via an RTSP stream. It is processing the stream and counting the people, and then pushing all the all the detections to a task, from where a user interface is used to A, show the results, and B, configure for each bus stuff like counting lines or areas. So let's have a look at the user interface for configuration. In this case, we have an image of configuration for traffic, and what you can see is you can paint basically a restricted area on that, and when you do that and click on store, this will be deployed to the edge device, and you will get automated alerts if a vehicle enters the restricted area. What you could also do is create counting lines, like a counting line, for example, here. So every vehicle that passes this counting line would be counted, and it works basically the same way for counting persons in the bus. In the end, it looks like this basically. You see people are being detected and being counted. In the top left, you can always see the counters for each door, for the door 1, which is the front door, and door 2, which is the back door. And you can also see some green boxes here, which represent the seats. So you can see which seats are occupied currently. Um, the inference is then, or the data that has been inferred, is then transmitted to the cloud, where you can see it on a dashboard. In this case, where the bus currently is, on the left side, how many people have entered, how many people have exited, and also how many objects have entered and exited, which is for luggage in case of unattended luggage if someone left the luggage. And what you can also see from seat detection, how many seats are available and how many seats are occupied. Okay, so let's have a look at the second use case. The second use case is the similar architecture, but this time in the campus edge network and with an edge server. So the camera stream is transferred to the edge server, and the metadata is then transferred to the cloud. Imagine we have a shop floor, and there is a laser welding robot that is autonomously welding parts together. It's assembling basically metal parts using laser welding. And it's critical that these laser welds are basically perfect. So what has been previously done, they sampled from all the welds, and then in a destructive process with laser technology and CT, they manually tested samples of the welds to see if the quality is still good. However, as this is destructive, it can only be done on a sample basis, because the weld is destroyed after that and cannot be used. So what we did is create a process for visual inspection of the welding process. That means that a camera is mounted to the welding robot, and then making images of the process, 70 images per second, that have to be inferred in real time and 24/7. So the challenges we had is we needed really low latency, a 24/7 availability, the possibility of retraining and redeployment, meaning that experts uh, are looking at the data, are looking at possible issues, then labeling them and redeploy a newly trained model. It needed to have very high accuracy, and we had 4 models for different variants of failure indicators, and that all in real time needs to be processed on an edge server. So what it looked like is basically a camera that streams about 70 frames per second to the EdgeML platform, where it is processed, and then the decision on if there are quality issues are derived by different models, one for splatter detection, one for well-through detection, for surface pores, for weld width models. And it's not only object detection, but it's also based on the time series of images that we had in the process. So in the end, you get the output if there are any issues with this weld predicted on the basis of multiple models with metadata. And inside this EdgeML platform, it basically runs on Nvidia DeepStream on a Kubernetes cluster with redundant hardware and GPUs, and in the background, our deep learning factory, which is our solution to all the ML ops topics, where you use historical data and you standardize components to retrain models and use continuous integration and continuous deployment to deploy new models after new data is available to the EdgeML platform. What can we take away from that? First, edge computing and 5G connects data and applications in real time. It enables completely new use cases like remotely controlled AGVs. Second, it's not cloud or edge. For a rising amount of applications, it's cloud and edge. We as T-Systems help our customers to succeed end to end. And third, AI is not just about ML. It's about the whole integrated system with latency and privacy requirements. So we as T-Systems are focusing on industrial applications with business users in mind. Do you have any questions or comments? Then get in contact with us either by dropping us a message in the chat or via email or via phone, whatever you want.